So we start and James, please.
Okay, thank you. So I was going to have some great big power trip at the start where I moved everyone on that side over to here, but it seems naturally everyone has already moved over to this side, so that's good. So just to give you a bit of an overview, I'm going to give two talks on quite separate topics. The first half is going to be about very thin films of gas and how we can describe them, and the second half is going to be on very thin films of liquid. And the kind of unifying thing is that we're at very, very small scales, and at these small scales, additional effects come into play. So very crudely, all my research is Navier-Stokes plus some small scale stuff. That's basically the summary. So in both cases, we're going to have a combination of fluid dynamics, interfaces, and lubrication. So I can probably speed through a bit of the background because this is very similar to stuff Darren and Dimitrios talked about yesterday. And then I'm going to be interested in these extra bits, none of which I'm an expert in, but hopefully I'll be able to teach you something which you'll find interesting. So the first is gas kinetic effects, which obviously appear only when we have a gas, so that's going to be what I'm talking about in a minute. Then for liquids, we're going to be interested in how to incorporate thermal fluctuations within standard kind of framework. And in both cases, we're going to find that disjoining pressure has some influence. And so what I want to do is go into a bit of detail in the first half, talking about how to think about these two, and then in the second half, these thermal fluctuations as well. Any questions, just stop me, and I'll happily attempt to answer them. And if not, I'll say something about, we'll talk about this in the coffee break. That means I don't know the answer. Okay, so droplets in action. We don't probably need to motivate this so much because we're here, but I just thought I'd mention a few because it's the standard thing to do. So one thing I worked on a little while ago was thermal management. So that's the idea of how to cool things down. And one thing that was being explored there was coating pipes or surfaces with superhydrophobic coatings like this one. And what happens then is very, very small drops meet neighbours, coalesce and jump off these surfaces. And the idea there, so that here you see some drops coalescing and jumping, or maybe not, the video's not playing, but the idea there is that these drops remove heat from surfaces. Something else we've been looking at is 3D printing of metals. So 3D printing of polymers and other things is quite common, but printing metals poses a much larger challenge because you have to heat these metals up to 1,000 degrees, and the problem is the instant they touch the substrate, they basically solidify. And so although you can create very beautiful looking objects like this, if you sneeze near it, it'll fall apart because it's not well bonded. So this was a really interesting project because these are very, very small drops, they're micro drops, and so experimentally it's very difficult to actually see what's going on. Instead, you can't see inside the drops, so it's somewhere that modelling can really play a role. Leidenfrost effect I'll talk about a little bit later if I have time. This is the effect that when you impact a drop on a very hot solid, it evaporates so strongly that it never touches that solid. It kind of levitates on its own vapour thrust, as it were. And that's bad news if you want to spray cool something, so you want to spray a liquid at it, at a hot surface. You want the drops to touch that surface, you want them to evaporate and cool the whole thing down. If it never touches, then there's no real heat transfer. So there's lots of cases where droplets and gases and all these things interact, and often they occur on very small, fast time scales. Sometimes we'd like to see inside these drops and we can't, and so there's a real kind of opening there for mathematics and computational modelling to play a role hand in hand with experiments. Okay, so what the kind of processes I've talked about here are drops impacting solids, drops impacting other drops. You could think here about, for example, drops in a cloud, and drops impacting solids and spreading across them, so wetting. And the simple question I'm going to be thinking about today is whether these drops merge with the surface or whether they bounce off. So here you see a case where these drops collide. These are maybe 100 microns, and they just bounce off each other. And the reason they bounce off each other is that in here is very, very thin film of gas, and it lubricates the contact, and they just bounce off each other. And the only thing I would like to know is if I fire two drops together of some size, some impact speed, are they going to merge or not? And that, as we'll see, is a surprisingly difficult question to answer. Okay, and this is about how fast essentially liquids can spread across solids before some transition happens, such as a splash. So in all these cases, we have very, very thin films of gas playing a rather dramatic role. Okay, so what the first half of this talk, the kind of educational bit, is going to be about how we can model very thin layers of gas. And then I'm basically, in the latter part, I'm going to go through some research topics where we apply that knowledge, and we'll see how long we've got and see how many topics we can get through. The other one is the Leidenfrost effect, slightly different because we have a hot solid here. These are kind of isothermal problems, and this one involves evaporation. Similar mechanisms. Okay, so some kind of very brief history of this topic of liquid droplets interacting with gas films. Reynolds notes in 1881 that droplets can skate across a surface before a few seconds before merging. You can see this in the shower. You have a shower, you look down, there's a film of water on the floor, and you see little drops flying around. And that's this phenomenon. But he believed that air was unimportant to the dynamics. Rayleigh, on the other hand, was looking at drops in a jet, and he says that whether the air can be anywhere squeezed out during the short time over which the collision extends basically dictates whether they coalesce. And that's precisely the correct mechanism. Can we squeeze out this air before the drops rebound, essentially? That's the whole crux of everything. It's kind of ironic, of course, because Reynolds is the person who wrote down the lubrication equations, which we're now going to use. So. Okay, so just to show you, and an excuse to play a beautiful video about how easily we can see how the gas plays a role, I'm going to show you some experiments from a French group and kind of pioneering experiments by Couder. A very simple setup. I'll just shut up and let you watch because everything's there. Run this in a vacuum, and you would see that the drops would instantly coalesce. And in fact, people have done that for drop-drop collisions. Very simple demonstration that it's the air that matters. Yeah, I'm afraid we've got to go back to maths. Sorry about that. Okay, let's get. So as I said, I'm going to do the educational bit. We'll see how long that takes, and then at the end, I'll force you to look through some of the things I've published. Okay, so fluid dynamics. Probably we don't need to spend a lot of time talking about this, but just to get kind of notational things sorted for now and for later. Throughout, I'm going to be interested in incompressible Navier-Stokes. So we have a divergence free velocity, and then we have conservation of momentum. We have F equals ma, forces on the right, internal forces and external forces, and this acceleration term on the left-hand side. And we're going to consider a Newtonian fluid, so that we have a stress tensor which looks like this, or with a viscous part that looks like this. Nothing overly exciting so far. So, I mean, you all know this, but the remarkable thing is that this set of equations works for almost everything. So, I mean, you can think of very, very small scale flows like an inkjet printer. You can think of large-scale flows like the weather, slow flows like glaciers, fast flows like aeronautics. And the surprise is, I mean, it's the situation where it's surprising when it doesn't work. It's more kind of surprising than when it does work. Okay, So interfaces we've spoken a lot about yesterday, so we've been introduced to surface tension. I'll just show you another video because I like this video. I don't know how many of you have seen these, but these are videos from the 60s, and in my opinion, they're still the best videos. They're the ones I always show in undergraduates, and I'm always amazed by how neat the presentation at the board is. It puts my board presentation to absolute shame because there's a reason I'm using PowerPoint. Okay, so surface tension and fluid mechanics.
Let's start with an idea that surfaces exert forces. It's not a new idea. It's a hypothesis, a successful hypothesis that explains many of the things that liquids do. I can demonstrate these forces by catching a soap film on a wire frame. The fact that the tension in the film is uniform in all directions explains the circular arc of the thread. To enlarge the film, I must do work. Force times distance. Pulling down the thread increases the area, takes energy to pull more molecules up into the surface. Another example of the pull of surfaces is given by a loop of thread placed on water.
This is what Demetrius was talking about yesterday, this idea of surface tension gradients.
Soap molecules lower the surface tension of water.
And so there's more of a pull from the outside.
The higher pull of the outer surface pulls the loop into a circle. The second boundary condition comes from a force balance across surfaces. One finds that a curved liquid surface has a higher pressure on the concave side. For example,
this is my favourite. This like
the higher pressure inside
and the 20s, I
forces
think.
the smoke out.
Obviously we bake now.
The energy of the surface becomes converted to the kinetic energy of the smoke.
So we've gone through all that already. Demetrios talked yesterday about a boundary condition, and in equilibrium we just have that there is a pressure jump across an interface, which is the surface tension times the curvature. And we have principal radii of curvature. If it's just 2D, we only have one, like this, which is pulling the interface down in that case. Okay, so now on to lubrication again. Fortunately, it's already been covered in quite a lot of detail. I'm going to be talking about lubrication both now and after the break, but in slightly different. Well, this is kind of lubrication and this is thin film equation. So the slight difference is here, in a sense, I know the height of the film from this drop coming down, and I want to calculate the pressure that this film exerts on the drop. So that's like a lubrication problem. Later, I know the pressure on the boundary because it comes from surface tension, but I don't know the height. So in a sense, they're the same problem, but slightly different ways of thinking about it. Okay. So I'm thinking about this drop flying down, approaching a solid for sake of argument, or it could be a liquid surface or anything. I just want to kind of motivate the idea. And roughly, I want to know the forces acting on this drop. So that is, in lubrication, the dominant forces will be a pressure and a shear stress. Okay, so these are the things which I need my lubrication model to give me when I input the height. So let's develop a lubrication model for this, and I'm going to do it for drop on solid and later show you that to do drop on drop is basically a very small change in the mass. Okay, so I'm going to think about an axis symmetric collision. So I've got a drop coming down vertically with gravity hitting a solid, and I have some coordinate system set up, cylindrical polar coordinates with a radial coordinate. My height then is just a function of the radius and time. So if I take in compressibility and I integrate it across this channel, then I get this conservation law, which is not closed because I have here the flux, which is the integral of the velocity across the channel. So this should be from 0 to h, essentially. So I have this balance of something squeezing, which is the HDT, coming down, in this case, minus the HDT, And that better be, because it's incompressible, that better be balanced by something flying outside. And so now we need to obtain this, and obviously we've used incompressibility, so now we need to use the momentum equations to find what this is. So it's a kind of relatively simple exercise to take what we looked at yesterday, take the very simplest lubrication limit where inertia is neglected because I'm interested in very, very thin films, so typically the Reynolds number is very small. We could build that in if we wanted to. And so I just have a balance of the radial pressure gradient and this viscous force coming across the channel. And then for a start, I'm just going to take the simplest kind of classic equations, no slip on the solid, and there's no slip here as well, except for this liquid is moving. So the speed of the gas, this UR, at the interface equals the speed of the liquid. Okay, and I don't know what that is at the moment, but I'm just going to call it something big UR. Okay, so I'm still capable of doing that amount of mathematics, just about, and that's the solution. So what are these two components? Do anyone know? What about this one? Correct flow, very good. What about this one? I mean, there's only so many flows, right? It's like when I ask my students, so what's the answer to this? 9 times out of 10, the answer is 0. It's never like 1.75.
Yeah.
Okay, so, Poisson flow, thank you. So I've got this linear thing and this parabolic thing. Okay? I can integrate these across the channel and still do the maths for that, and I get, again, a term from Poisson, which is this famous h cubed over 12 mu, and the correct thing. And I can work out the shear stress if I want it just by taking whatever the expression is for that. Okay, so what we've found is essentially this problem is equivalent to flow in a channel with a flat top and a flat bottom locally in some sense. And I have two terms which are Couette thing with no slip at the top and bottom and the Poisson thing. So the surface is moving is accounted for by Couette, and the pressure gradient gives me Poisson. And I can superimpose them because it's all linear. Okay. Everyone happy so far? Okay, so I know now the flux that I need is just these two bits added together, and I can see, I can see how does this flux compare to an experiment in precisely this geometry, except for I'm going to have a solid wall at the top and the bottom. Okay? So the experiment, and there are many, many repeats of this, but this is this one from UARTS in 2007 in JFM. I have a microchannel here, solid top and the bottom, roughly 2D, but not quite. I have a pressure here, which is presumably higher than the pressure here, that drives the flow through. I measure QR, how much mass goes through, and I compare it to experiments. So this is a case where UR is 0 because I have no slip at the top and bottom, so I'm only interested in the Poisson component. And what they want to do is they want to compute how this flux depends on the Knudsen number, which we haven't talked about yet, but we will in a bit. And the Knudsen number compares the height of this film, which is going to be fixed, to the mean free path in the gas. So the mean free path in the gas is how far, on average, does a molecule move before it collides with another molecule. And if everything's going to be in some kind of thermal equilibrium, we want lots of collisions to equilibrate everything. So when this is very, very small, so we have a huge height for our channel, we expect everything classical to work, Stokes flow, blah, blah, blah. When the height of the channel is comparable to this distance that molecules are travelling between collisions, something else might happen. Let's see. Okay, so to control the mean free path, they changed the pressure because the mean free path is inversely proportional to the pressure and the density. Okay, so this is their result. So this is Knudsen number on a semi-log plot against this QR value. So how does this compare to Navier-Stokes, or Stokes if you like? So this is the expression we've just derived. And you see it's pretty decent up here where you'd expect it to be, up to about Knudsen number 0.1. And down here, it's clearly a disaster, right? Interesting thing in the data you can just about see if you squint is that there's what's called a Knudsen minima. So this actually goes down and then back up. Okay. What's important for us is that when we're going to be looking at these impacting drops, the layers of gas which you get there are tens, hundreds of nanometers. So that is Knudsen numbers around here. And so we need a model which is going to capture this region. Okay, so let's talk now about gas kinetics of fire. Gas kinetic effects. Yes, go for it. Into which one? Into this one. It's a little bit tricky because it's a direct comparison to experiments, and the experiments vary the pressure gradient and the actual level of the pressure. So I can show you where the paper is. But it is very confusing, I agree. Yeah.
Because it's not showing the actual formula.
It's not obvious, right? You look at it and you think h cubed, so it should go like, but it doesn't, yeah. So it's not obvious, and it was just basically, I took the data from there and plugged it into this formula. But it's for a fixed h. So it's this PDR thing which is varying. So they change both the gradient and the level of the pressure. Because it's the level which fixes the mean free path and the gradient which fixes the flux. So it's a bit mixed up. Good question, thank you. Okay, so gas kinetic effects. The idea essentially is here, if we want to solve gas flows on small scales, we need to solve the Boltzmann equation. We don't want to do that. So what I want to show you is that when we're in a lubrication framework, there are ways to incorporate the Boltzmann type results into our framework in a relatively easy way. And when we get outside lubrication, things are a lot harder. Okay? So first of all, the first kind of failure of our approach occurs near boundaries. So near a boundary, we always have what's called a Knudsen layer, which is the thickness of the mean free path, so about 100 nanometers for air in this room. And in there, crudely, Navier-Stokes is inaccurate. And that's because we don't have enough collisions to equilibrate everything and for Navier-Stokes assumptions to be valid. So we could imagine some flow profile where everything here is described by Navier-Stokes, and then we have a boundary layer where Navier-Stokes fails. And the dimensionless thing characterizing all this, which I've already mentioned, is the Knudsen number, and that's the mean free path divided by some characteristic height, which is going to be our film height. Now, when this number is much less than 1, so maybe less than 0.1, we can attribute all this horrible boundary layer stuff into a boundary condition. Okay? So all we do is, I mean, it looks like I'm cooking this out of thin air, but from the Boltzmann equation we can derive this equation. This equation is a slip condition, so it goes, if this is 0, we have no slip. But now this says that there is a jump between the velocity of the gas and the velocity of the solid, and the magnitude of that jump is the shear stress times what's known as a slip length. And the slip length here is basically the mean free path. This C depends on the collision model and various other things, but it's always about 1. And the nice thing about this is it connects the gas kinetic effects with the gas pressure, which we'll see is very important later for experiments. Okay, so if I decrease the pressure of my vacuum chamber or whatever I'm doing this experiment in, then I increase the mean free path, and that means more slippiness, more slip between the two surfaces. Okay, so we're still in something that can be done pretty easily. Our bulk equation is unchanged. We're going to modify our boundary condition to have slip. So if you remember the situation we were looking at, the top boundary was moving with speed UR. So that's my slip condition on the top boundary. And this is my slip condition on the solid, which wasn't moving, so there's no that term. Okay. So this slip condition is known as the Maxwell or the Navier condition, depending on your community. Quite often in liquids, people talk about Navier slip because it was postulated Maxwell derived this condition in gas dynamics, so it depends how you are. Okay, so show that. Okay, right, I've got 3 minutes. And I'll be walking around. Okay, so that's not hard to do to show this. It's just an extension of the previous condition we had, and if lambda goes to 0, we have the expression we had before. So we've found this condition, and we can still extract from it a Couette component, which now has some slippiness, and a Poiseuille component, which also has something like that. Okay. So we add these together again, we get a new expression for the mass flux, which we hope is more general and might extend our applicability a little bit. Remember, it's for Knudsen number much less than 1 still. Okay, so that was our expression. And what we see is that there is actually no additional Couette component, but there is an additional Poiseuille component, which is this term here, which is essentially a kind of enhancement of this factor here. Okay, this is the Knudsen number here. So what we're going to do later is we're going to talk about incorporating this enhancement factor into the viscosity and calling that an effective viscosity, but I'll come to that in a bit. Okay, shear stress, blah, blah, blah. Okay, I'm going to talk about that now. So a nice way to write these things and to think about them is to think about an effective viscosity. So here, that's the real viscosity. The real viscosity doesn't depend on the pressure in the gas. Okay? So that just has some value, which is whatever it is, 1.8 times 10 to the minus 5 for air at atmospheric pressure. This thing depends on the Knudsen number. So all I do is I introduce an effective viscosity, which depends on the Knudsen number, and it appears here. So the expression now looks the same, but with this effective thing, which depends on the Knudsen number. And I like it because it just gives you a picture. We all have a picture of what the viscosity does. You know, high viscosity, it's hard to push something through a channel. So if I'm lowering the viscosity, it's going to be easier. So you can see now, a higher Knudsen number is going to reduce the effective viscosity. So compared to Navier-Stokes, it will be easier to push stuff through a channel. Okay, so I've spoiled this question, which I realised when I was saying. It's a bit of a trick question. So is it easier or harder to remove gas from small channels? It's harder, right? So it's still harder because h cubed is here. But with slip, it's easier to remove gas than without slip. Okay, so the model predicts more flux for a given pressure gradient at a given channel height. Okay, so these are expressions, blah, blah, blah. For Knudsen number 0, we're back to where we were before. Okay, so I should say there's a similar one for the Couette flow, which is different from the Poiseuille flow. This was what... Yes, Sasha?
No, I have a question.
Oh, okay, sorry.
So you said that the Couette flow doesn't change. Is that just the QR that doesn't change? Or are you saying the viscosities?
The profile shifts, but because it's symmetric, you don't get any extra flux.
Okay, but
So
you're still changing the stress of the boundary.
The stress changes, yes. So the stress comes in here. So you see the Poiseuille stress doesn't change, the Couette stress does change, and it reduces.
Okay.
Because it's more slippery in some sense. You can imagine the gradient decreases, and so this.
So it's like different physical processes
With
the different effect for the different flows.
It's the same physical process, but because it all comes from gas dynamics essentially, but they have different effects because one's linear, one's parabolic essentially. So the Couette thing is symmetric and therefore you can't have an extra flux. It's like It's almost like, you know, when you take correct flow and you go like that, and then you ask the students what's the mass flux, and they spend 3 hours deriving it, and you say, well, by symmetry it's actually 0, but well done for deriving it. It's that kind of idea. Any other questions? So this was what we had. This was failing about here, and this is with slip. Okay, so you can see why people want to incorporate slip, because it's not a huge amount of extra work, and now we're up to 1-ish with a reasonable result for the flux. As I said, we would actually need to go even higher. The gas films which we're going to encounter genuinely go down to 10 nanometers, and so we want something even better, we're being selfish. Okay, so when Knudsen number is 1, or 10 even, this idea that there's a boundary layer where things are nasty just goes out the window, and the whole channel is out of equilibrium, and so we need solutions to the Boltzmann equation. And there is a massive body of literature on this problem, because it's a very big problem, 70s, 80s, in micro-electromechanical systems where you have lubrication, very thin layers of gas between moving parts, and the obvious thing to do there is to calculate the forces and the fluxes associated with channel flow. So everything, when we came to this, everything was already there. It just hadn't really been applied very much to liquid problems. So what we know is we've just derived an expression for Knudsen number going to 0 with slip. And there is also an analytic expression for Knudsen number going to infinity, which is free molecular flow. So that's when there are essentially, it's the limit in which there are no collisions in the bulk, all the collisions are with the boundary. Okay, it's almost like a kind of... Okay, and what I'm going to show you in a minute is that with a fit to Boltzmann solutions in between, we can derive expressions for this effective viscosity, which hold for all Knudsen numbers. Okay. So let me show you how that's done. So for the Poisson coefficient, we know, I talked about this effective viscosity before for slip. In the literature, you can find an expression for Knudsen number large, an analytic expression for Boltzmann equation, which is this. And in between we can do many, many different things. We could solve the Boltzmann equation. It's not so difficult. It's essentially a 1D channel flow. It involves integrals over exponentials, which you can do, which is what I did originally. Or you can just say, actually, we have this limit, and in between, the Boltzmann equation has been solved in this geometry a million times. So this is data from solutions to the Boltzmann equation. And so we can just basically fit in between, and that's what we've done. So this expression has this limit for small Knudsen number, this limit for large Knudsen number, and we just put in an extra term which means it fits in between. Okay, and that's why things are easy in this lubrication geometry. We want this, the only thing that varies are these two effective coefficients, and all they depend on is the Knudsen number. Okay, so yes, we can make things a lot more difficult. So for example, we could have the top surface at a different temperature from the bottom surface. We could have the top surface with diffuse reflection, the bottom surface with specular reflection. And we can make this a function of many variables, but the principles still hold. Okay, so the final thing is this expression which I've just derived. And you see now we're getting decent results for the full range of Knudsen numbers. Okay, so to summarise, we have incompressibility which gave us this, and we have a flux, the form of which we derived for Stokes flow with no slip, and then we added slip and saw some changes to this. And finally, we can incorporate all the Boltzmann type stuff into this effective viscosity.
James?
Yes?
So that 2.76 and 0, are they curve fitting?
Well, I think one of them's curve fitting and one of them comes from the limit.
Okay.
Certainly one. I think it's, yeah, I can't remember which to do. You can see this one is the slip.
Yeah.
Then one of these terms is the free molecular flow limit. I can't remember which one. And the other one is fitting. Yeah.
James, I'm not sure you mentioned that normally we think that air is less viscous than water, right?
Agreed so far.
Yeah, but actually the viscosity coefficient is higher for air. Is it right?
I mean, I'm talking about dynamic viscosity. You're talking about kinematic viscosity.
Viscosity which represents the model.
This dynamic viscosity for air will, I mean, I can show you, did I plot it somewhere?
Yeah, just values.
Here I showed you.
So
So
argue that indeed we need viscosity for air.
for air, the viscosity is 1.8 times 10 to the minus 5 at atmospheric pressure. And then as you go to
Water.
water is 10 to the minus 3, right? So water is up there.
Okay. So the air is still less viscous
Yes.
than water.
Yes.
But actually, in many models, we use the viscous model for air and inviscid for water. Is it right?
Well, it depends on the Reynolds number, right?
Depends on the element number. Many. That is interesting.
Sure.
It's not intuitively clear why we are doing it.
Yeah. So I normally, when I give this, when I give this as a kind of research talk, I normally start by talking about how the traditional assumption is to ignore the air. Because, you know, you look at the viscosity of the liquid, it's many, many times larger than the viscosity of the gas. You look at the density of the liquid, it's many, many times larger than the density of the gas, so who cares about the air? And then I'll show you some experiments in a little bit where we see how important the air is.
Yeah, and also I believe the size is very important.
Sure.
If you go to the ship hydrodynamics or offshore hydrodynamics, the size of meters,
Yes.
right, the same effect can be observed. But there, the modeling is completely different.
Yes.
And there is the most important is instability at the water interface, right?
Yeah.
Because there, as I understand in your lecture, there will be no instability because of shear.
That's right, yeah.
Yeah.
So,
But in other experiments, it's very visible. So this is the very unstable process, right?
Yeah.
So that is good to.
Yeah, for sure. And the steps kind of beyond this are to incorporate compressibility and inertia, which I'm not talking about. In the problems you're talking about, this is an inertia dominated in the gas as well, right? Yeah. There's a very good annual review, I believe, on ship dynamics from maybe the 80s or 90s, Sasha. Did you write that one?
No. I can add that. Sorry for interrupting you. But when I was the master student, I was employed by my supervisor for many years to do a review on what you said about the dependence of viscosity on pressure.
Okay. There you go.
And because I couldn't find many that time, many papers, so I did my own research. So I'm very pleased that it still survived. No, it was not published, no, it was just internal report.
Okay.
I mean, the report for class.
I see.
But it's very good.
Anything else?
More stories.
Yeah, more stories. Okay, so where were we? So we're done with that. We've got a model. We've got all our effective viscosities. And, I mean, things are pretty simple, right? I mean, this is the simplest lubrication model. We just have a formula which depends on Kutzen number. Kutzen number can change either because the height changes, so it's something which will change locally, or because the mean-free path changes because we reduce the pressure in the gas. So I told you I'd talk about head-on drop-drop collisions. So head-on collisions is my new favourite because the classic question, I'm going to say it so nobody even asks it me, it is, what about the roughness of the solid? Which is a very good question because most solids are, of course, rough. So if I'm interested in a 10 nanometer gas film and I have a solid which has roughness of 10 microns, then this is all a bit relevant. In contrast, drop surfaces are very smooth. So drop-drop collisions in the kind of most natural state, you know, think about contacting clouds and development of rain, we have very smooth surfaces and we have very thin films naturally. So the model here is slightly different. You have now, if we consider head-on collision of two identical drops, just to build things up simply, we don't have Couette anymore because there's no slip solid. We have plug flow instead, and we still have pressure gradients. Okay, so the model looks almost the same. This is the same. There's a factor of 2 here, and there's a 0 here because there's no shear due to Couette. So basically, if you can do one, you can do the other computation techniques. Okay, so let's now start thinking about applying this knowledge to the impact of droplets. So a lot of the early work from the late 50s and the 60s was thinking about clouds, drops merging. So this perhaps isn't quite the right picture there. The picture there is a big drop falling through a cloud and collecting lots of drops underneath it. So typically those drops are very small, so people started thinking, well, can't do this on a computer, we're in the 50s, so I'm going to consider a rigid sphere, which means that it's both a sphere, remains spherical, and you have no slip on the surface, because the liquid is more viscous than the gas. So what you find if you do this is this kind of Stokes paradox over it again, where you have a singular force due to lubrication when these two drops approach each other, which goes like 1 over h, and so the drops never touch. Okay, and yet you can see, you can fire two drops at each other and they will merge in certain circumstances. So some issue with Navier-Stokes and no slip. So Davis and Hocking in the early 70s put in slip conditions, which I've talked about, so you now know what they are, and showed that that permits contact of these drops in a finite time. There's then work in the 90s and noughties by Donald Cox group, where they use essentially the third model I showed you, which is this Boltzmann type lubrication in between this gap. So there's been a lot of development in that literature on incorporating gas kinetic effects. What about computations? So for Navier-Stokes and this kind of no-slip lubrication, we know that these drops should never merge. In fact, when they deform, things become even worse because essentially you get two flat interfaces approaching each other, and the lubrication force is even stronger than having two curved interfaces approaching each other. So these drops should never merge. So there are so many papers in the literature basically saying the same thing, and that is that, so this is one by Navier and Vassen, which is doing some front tracking simulations. They look at drops impacting, they compare two experiments, and they say the principal weakness in the simulations is the ad hoc way the film between the drops is ruptured. What's super interesting with this, so there are other problems where you can do something a bit dodgy and get away with it. This is not one of those cases because you have to choose, in these simulations, they choose the time and the position at which these drops merge. And then, depending on that choice, so these are two different choices, they get completely different outcomes after they've merged. So it's not just a case of, oh, let's just make them join and then everything will be fine. It's literally how they join changes everything. Okay, and there's nothing in this model which will let them join. What we've found more recently is that if we put Navier-Stokes, so my big dream for this was, well, let's just put gas kinetic effects in and they'll join. And what we found is that they still don't join. The drops become a lot closer because of this kind of reduced viscosity, but they still mathematically never join. Okay? So there still appears to be something missing to pull these interfaces together. So I just built up the narrative to this wonderful moment where we're all thinking, what is that extra effect which is going to bring the interfaces together? I can tell. And that extra effect is disjoining pressure. And let me explain what that is. So the disjoining pressure is essentially the extra force we get from the molecules in the solid being attracted to the molecules in the liquid. And probably, maybe you've seen this expression written down. The disjoining pressure gives an extra pressure in the film, which is Hammaker constant A divided by 6 pi h cubed. So this depends on the materials. And what it means is that if the film gets thinner, there is a higher pressure there, and so that will drive flow out of that region and further enhance the chances of contact. So it's the extra force which is going to bring these interfaces together. And what's kind of cool is that we started adding this just because we were annoyed that the interfaces wouldn't go together, so we're like, well, let's add that. But it actually brings with it some additional physics, which hopefully I'll have time to talk about towards the end. Okay, so this is a force which competes against surface tension. Surface tension doesn't want this wave in the interface, it wants to flatten the whole thing. Disjoining pressure wants to pull this together, and disjoining pressure will win for long wavelengths. Okay, so there's a critical kind of wavelength associated with this instability. So I thought I'd just go through it and sketch out. Sketch out is translation for me saying, don't ask me any difficult questions. Where this expression comes from, because I think personally I'd seen this and I knew in a kind of hand-wavy sense where it came from, but I'd never derived it. Okay, so we can think about attraction and interaction potential, kind of energy between molecules, and the one which is commonly written down, which comes from long-range van der Waals amongst other effects, is that the energy is 1 over the distance between the molecules to the power of 6. So that's what you'd have for a Leonard-Jones interaction, which is the most basic interaction you can think of. And then we're thinking about a number of molecules, ns per unit volume, in both the liquid and the solid. And what we want to do is we don't want to know what the individual interaction is, we want to know what happens when we've got all of them, and sum them up. Yes, Sasha? Did you do this in the 60s as well?
Sorry. Is it related to van der Waals?
Yes.
Did you mention?
Yes.
Okay, so I missed it.
Okay, yeah, so this could be that dipole would be the simplest thing that would give you this.
Okay.
But there are other.
But then the that power actually comes from the Waals?
Yes.
Because there are
The 6 comes from van der Waals, yeah.
yeah.
Okay. Right. So what are we going to do? So first of all, we're going to take a molecule in the liquid and work out what is the forces between it and a portion with a number of molecules per unit volume of the solid. And so to do that, it makes sense to use cylindrical polars, so we can basically, we're thinking about an infinite volume here and infinite volume here to start. So this is the distance between this and this, which we can work out from simple algebra. And then we integrate over radius, over z, and over theta around here. And we have a number per unit volume, and that gives us energy of interaction of this with the whole solid. Okay, so that's relatively simple to do. Then we integrate up here. So we now integrate from h to infinity over all the liquid molecules. But we want the interaction energy per unit area. So we want it at a given height. We don't want to take out all of the angles, if that makes sense. Okay, and that gives us this expression, 4 pi squared times this interaction thing which came from the d to the 6 times the density, so that makes sense, right? If there's more molecules in here or more molecules in here, the energy is going to be larger. And then this is basically what the maths has shown us. And this ALS then is 4 pi squared CLS MLS. In reality, this is something which we just calculate experimentally normally. Okay, so that's the energy, and from the pressure, we just basically have the EDH. Okay, and that gives us the 2, comes up here, and gets 6. Okay, so hopefully you have some idea where that comes from. Okay, so how do we modify our equations? Well, we just basically redefine the pressure as we would if we had like gravity or something like that. We just redefine the pressure. It's incompressible, so we don't need to worry about that. And our pressure now has this additional term, and we know that this additional term is going to pull interfaces together. So the unconventional aspects here are both gas kinetic effects coming in through viscosity, effective viscosity, and disjoining pressure. Okay, so on to the research bit. So we'll see how long I've got. 25 minutes to go. Any questions before I start? So this is what I've already mentioned. It's easy to convince yourself that the air shouldn't matter. The viscosity of a droplet is many times larger than air, even something with low viscosity like water, and the density is many times larger. If we believe this, that the air shouldn't matter, then certainly if we change the pressure of the air, that shouldn't really affect anything. And if we change the type of gas, it shouldn't really change anything. So if we, instead of doing it in air, if we did it in helium, nothing should change. So what I want to do is show you from experiments that the gas matters, explain why the model requires this previous 55 minutes of your life. It would be a bit disappointing if it didn't, right? And I want to show you actually it's easy to do. That's why I want to convince you it's not like something scary and hard. It's something that can be done relatively easily. Okay, so experiments. So some of the earliest experiments, Sasha, you might have some experiments which maybe aren't as early as the one Sasha knows, on drops, showed this interesting effect of a little bubble appearing underneath them after impact. And in the early papers, in Chandra and Avedisian, they talk about this could be due to cavitation, or it could be due to a lubricating gas film deforming this drop when it comes down and trapping a bubble inside. And we now know it's very much this second thing which matters. So people like Sigrid Thoroddsen have done a huge amount of work characterising this trapped bubble, and it's relatively well understood. What's interesting is that there's this kind of drop-solid community, and there's a completely different drop-drop community who are kind of interested in combustion chambers and sprays and applications in meteorology. And we've seen already that these are mathematically very similar problems, but the two communities are almost completely detached. So there, in the late 90s, there's this paper, which I still believe is the best drop-drop paper. What they show is you fire two drops together, they're about 100 microns tetradecane. You fire them together slowly, they'll merge. If you fire them together a bit faster, they bounce off each other, and you go even faster and they merge again. Okay, so it's like this kind of miracle. You have these two transitions. And any theory which we develop, we want to predict these two transitions between merging and bouncing. They then did this experiment in a vacuum chamber, so they varied the pressure, so they actually increased the pressure here. And what that does is it shifts these transitions around. In the drop-solid community, there's this kind of amazing result in 2005 by Sid Nagel's group in Chicago. And what they did is an experiment where essentially they expected nothing to happen. They impact a drop at ambient pressure, they impact it at reduced pressure, but not by a huge amount, maybe a factor of 3. And you see completely different behaviour. So the idea here that the gas is some kind of secondary thing we don't need to worry about, it goes out the window, because changing the gas pressure can suppress a splash. Okay, and so this is the quote from their paper. Okay, so as a result of this discovery, there was a huge amount of research into trying to understand how does the gas affect the drop. So option 1 is this drop comes down, it doesn't touch the solid, there's this lubricating gas film, and somehow that affects the splash. Option 2 is that it comes down, this has a roll and it traps a gas bubble. This thing then starts to spread, and it's this spreading process, this wetting process, that changes whether it splashes or not. Okay. And if we have time, I'll tell you which it is. Okay, so as a result of this discovery, lots of people started doing experiments where they started looking underneath the substrate at drop impact so they could resolve the film dynamics. Okay, so in 2011, 2012, all these PRLs, everyone started thinking about this gas film using internal reflection and interferometry and various other techniques. As a result of this, I believe, there was then a discovery in around 2014 by two different groups that if you have sufficiently smooth surfaces, I'm sorry about this, it's not quite bright enough, is it? Can you see it at all? Or? There's a drop here. I'll be the drop. The drop bouncing. That's all right. Thanks for trying. So it's cool, right? Very rough. Lots of people knew about this. This is a super hydrophobic surface. The drop comes down, it spreads over the pillars of some surface, and it rebounds. Here, the drop never touches the solid. But how do we know? Right? And that's partly why people started looking underneath the surface and using things like internal reflection. So in this case, you can see dark areas are where the film is thin. So there's a bubble trapped in the centre. You see this drop spreading, this is underneath, and in this case it will never touch the solid. But you really need to look underneath to be able to see whether it actually touches or not. And this is another interesting kind of comparison between drop-drop and drop-solid. In drop-drop collisions, you can't see the film. You can't, as far as I know, nobody's been able to visualise this because, you know, you can't look inside two drops colliding. It's a challenge to experimentalists. Okay, so for sufficiently high speeds, this drop will touch down. So there's a critical speed again, just like the drop-drop collisions. And what's interesting is that the original experiments, Kalinsky said that the film height just before touchdown is around 2 nanometers. And De Ruyter group said it's around 200 nanometers. Quite a discrepancy in the predictions, and that's something which we'll be able to predict. Okay, so what's broadly accepted is that the gas is described by viscous lubrication theory. As I'll show you in a minute, these are genuinely long, thin films. You know, they're like 100 nanometers high, maybe 1 millimeter wide. So lubrication theory is reasonable. And what is clear is that the usual formulation fails. Okay? And that's because the only parameter in the usual formulation is the viscosity of the gas. So if I change, for example, the ambient pressure of the gas, nothing changes. Okay? Because the viscosity doesn't depend on the ambient pressure. Okay, so something's missing in this standard model. And lots of people have come up with various ideas, some inertia, compressibility, evaporative cooling. And no doubt all of these play a role in some cases. So for higher impact speeds, for example, compressibility is likely to matter, inertia might be. But for the lower impact speeds, especially these drop bouncing things, what we think is that gas kinetic effects, fortunately, given that 55 minutes, are the most important effect. So other people have incorporated these into models for drop-drop, drop-solid, high-speed wetting, drop-on-solid, etc. So just to finally convince you about how thin these films really get, this is a drop-on-solid case. The film heights in here, I'll explain how to read this map in a minute. For now, all you need to see is the colour bar. This is the film height. It certainly reaches 100 nanometers, and that is Knudsen number 1. Okay? So we need models at least that do Knudsen number 1. Okay. So a really nice article, one of the first articles to incorporate gas kinetic effects into drop-drop collisions. Computation is by G. Lee, who's in Cambridge, and he uses axisymmetric finite elements, or uses an axisymmetric assumption and then finite elements, and he was able to describe the shapes, so his black lines are computations and the experiments in the middle perfectly. the one take-home message I want to give you is that if you see a code which produces pictures of two drops colliding and bouncing off each other, that is really easy to do. You go away, if you use COMSOL, you use ANSYS, you use Basilis, whatever you want, and you tell the drops somehow don't touch. So you say, I don't know, computation, you can say, well, don't allow merging, or you say pressure is inversely proportional to the 73rd power of the height, whatever you like. You will produce these images perfectly. Okay? The hard part is to produce the transitions between bouncing and merging. And this is the first paper that really did that. People then thought, well, it's been done axisymmetrically. Unfortunately, head-on collisions of drops is not hugely likely. Can't tell clouds to just make sure all collisions are head-on because we're in a maths department and we like axis symmetry. So the thought was, let's go to 3D. And there, things are very difficult. Things are still unsolved. Again, the same result which has been I've talked about before. If you tell the drops, don't merge, then you agree with experiments. You then have an experiment which merges and you tell the drops, oh, you can merge now, then you again agree with the experiment. But no predictive power because you need to tell it beforehand what's going to happen. Okay, so the challenges are, this is all in drop-drop, so we'd like to put gas kinetic effects in drop solid. I've already shown you how to do that, it's very easy. And there's a huge multi-scale challenge because the drop's a millimetre, the film's on the nanoscale, so this is 10 to the minus 3, this is 10 to the minus 8. 5 orders of magnitude, you've got a finite element in the drop and a finite element in the gas. And this is a big difference. And that's where lubrication is going to save us. So the two people who've done the most work on this are Nikita, who was my former postdoc, Peter, who's my current PhD student. I always put this QR code on because it looks trendy to have QR codes these days, but this is all open access in UMFLIP, which is a finite element framework. And so if you're at the start of your PhD and you're looking for a tool which is kind of developed, that's there and hopefully of use. So we've done the model already. This was the model we derived earlier. I can just change this F from 0 or 1, or 1 or 2, I can't remember which way around it is, for drop-drop or drop-solid. So F is 2 for drop-drop, F is 1 for drop-solid. And in the liquid, no dramas, just solve incompressible Navier-Stokes. So computationally, the kind of approaches people have used, people have thought about solving boundary integral approaches. So if you have Stokes flow, you can use boundary integral, you have fundamental solutions. If you have implicit flow, so you have like the Euler equations, you again have potential flow, we can write down fundamental solutions, and you can use boundary integral. So basically, instead of solving within the bulk, you solve a 1D problem around the boundary. And it's still tricky, but you can do it. And then that interacts with gas. The other option is the hardcore kind of computing option, which is along the lines of what you're going to learn on Thursday and Friday, I think. You mesh the whole thing Eulerian, where you have interfaces, you put lots of elements, and there, that's a real killer, because down here, you have to, if you want to resolve it, you need a million, you need this element here, this cell here to be 1,000,000 times smaller than this one. That might sound impossible, but it's not with adaptive meshing, and probably in the next few years people will be able to do that relatively routinely. But now imagine it's 3D, okay, and then you can start to understand how that's going to... Yes, Sasha?
Is it possible to kind of mimic the air layer thinner by special boundary condition for liquid?
I feel like you're teeing me up so I can smash it out of the park, Sasha. So the alternative approach is you can mimic the gas layer, and instead of actually resolving that, you just basically apply this lubrication as a boundary condition. Thanks, Sasha. Okay, so we have Navier-Stokes in the liquid. We capture the interface exactly because that makes it nice and easy to apply our lubrication. So along here, it might look like this drop is touching the solid, but it's not. There's a thin void, essentially. There's just nothing there. There's no elements or cells there. There is just a surface along which we apply our PDE. So the difference between the Lee's approach and previous approaches, they're incredibly complicated adaptive meshing so that this can shrink while this drop impacts. We just have meshed the drop and apply the boundary conditions along here. And it's fortuitous, right? Because lubrication, in this problem, there is only ever an effect from the gas when you have lubrication. And when you have lubrication, this approach is valid. So it's like this super fortuitous thing that, I mean, if in this case the pressure was important here, we'd be doomed. But it just so happens that because the pressure only happens when it's long and thin, and lubrication is valid when it's long and thin, everything works nicely. If it was a liquid-liquid or a gas bubble approaching another gas bubble, this would probably not work. Okay, so here are these pictures I told you to be aware of. We also can produce pictures of drops impacting drops, which agree perfectly. And now we can start to think about these various transitions I mentioned. So the first one we're going to consider is a relatively low impact. What you'll see here is the drops impacting at low speed. You'll see in here the film, because you won't be able to see what's going on in the film here, and then stretch it out and show it here. And then this is the minimum height, and why we care about the minimum height is when that goes to zero, the drops touch. Okay, so this is a case where it's just below the bounce merge transition. What does that mean? That means it's just fast enough that they will bounce. But you can see this, they remain relatively spherical at these low speeds. 2 points don't touch, so this gas bubble kind of almost trapped in the middle. And quite often at low speeds, they actually coalesce upon rebound. So at higher speeds, much more deformation. You have films forming along here, and quite often it's instabilities in the film caused by the disjoining pressure which bring these interfaces together. Okay.
How do you know it's instabilities?
Okay, good question. So what we do is we do these simulations and we see some wiggles. And I say, I don't like wiggles, Peter. You go away and get rid of the wiggles because they look like numerical artifacts. And then we do it again and we still see the wiggles. And then we're like, oh, well, maybe they're actually waves. Okay, and then what we do is linear stability analysis, where we take this long, thin film and we do all the kind of classical linear stability things, and we find a critical height, which depends on the disjoining pressure, surface tension, the time of the contact, and we see that agrees quite nicely with the simulations. So what we see is that when we go below that critical height, they join, and when they don't, they bounce. Okay? So it's kind of, the problem is this formula has absolutely zero predictive power because I don't know what the minimum height is. So if somebody can come along with a theory which tells me if I fire two drops together, this is the minimum height that the film in between them will reach, 10 nanometers, 100 nanometers, I can apply that formula and tell you whether they're joined. And we've tried various formulas in the literature because there has been a lot of work in this area. And to cut a long story short, none of them really agree with the critical height, the minimum heights we see. Because this is a case where it's Navier-Stokes in the liquid. Viscosity matters, density matters, everything matters. Maybe if it was a high impact speed, these theories might work slightly better. Okay, so this was the case we really wanted to look at, where we had these two transitions between merging and bouncing as we increase the speed. And this is the experimental data. This is our computational results. And so here, for example, you take a radius of 200 microns, you increase the speed a little bit, they will merge. Increase it a little bit more, they bounce. And increase it even more and they merge again. So you have these two transitions. This is called a soft transition and a hard transition. Small drops for head-on, they always merge. Okay, and this is a little bit of a cheat because here I'm going to talk about how the gas pressure affects the simulations, but in the simulations we can basically run the same simulation and plot the data twice by changing the definition of the Kutzen number. In experiments, though, what I'll show you is if we think of something dimensionless down here which depends on mean free path, then we can collapse the experiments. And again, the other question I always get, what about that data point there? That doesn't collapse. And the answer is, I've got no idea why that data point's there. So, I'm sorry if I've ruined all the questions. So this is basically collapsing all the data based on the mean free path of the gas. So these are for air and helium. So helium has 3 times roughly the mean free path of these. So what we then started looking at is how these drops contact. And there's been a lot of work in this on drop on solid, where you can actually see underneath where the drop contacts. Does it contact in the middle, or does it spread out and then contact, or does it come to rebound and then contact? All these different modes. But in drop-drop, you just can't see inside these drops. So we looked at different modes, and this is, what's this one? Contact position. So this means lighter colour means it contacts early, so it comes in very fast and contacts. This is where it spreads out a long way and then contacts near the edge. And you can do all these contact modes. Okay, so I'm running out of time, so I'm just going to kill you by PowerPoint for 2 minutes to say we've also done drop on solid, and we can agree nicely with the experiments I showed you earlier. I'm not going to leave you hanging about the question. So, as I told you, de Ruyter predicted that the height before contact was around 200 nanometers. Kalinski predicts 200 nanometers. Because we're diplomats, we predict 20 nanometers. And that's quite a reasonable value physically that van der Waals might kick in at around 10, 20 nanometers. So that's drop on solid. We also did some virtual experiments where we put drop bouncing into a vacuum chamber. And, okay, so these are the instabilities I was talking about. So you see wiggles like that which look horrible, but actually they're genuinely linear instabilities. And then someone did some experiments, which I'll show you the experiments because they're cool. So Ying, Sun's group in Drexel did some experiments trying to confirm this effective mean free path on drop impact. And this again will show you, if you watch these, you'll have no idea which one of these has touched the solid. But if you look at the film profiles, then you will see. This is very complicated. This apex comes down, jets through the centre and causes impact to the gas film here. It's a very kind of non-linear, wavy mechanism. Okay, so they all look the same, but this one's now touched down. And like I say, you have no idea looking at those. Obviously, eventually you'll find out because these two will bounce off the surface and this one will stay there. Okay, so we had some comparison with their models. We had a Zoom call with them, it was COVID-y, and they said, this is a disaster. This is your curve here, and this is our curve here. And I said, this is the best day ever. We're like, and my prediction is on the same page as your experiments. So we had a bit of a miscommunication. So I was very happy that the shapes were even the same. But the point is that their system is quite different because they're actually impacting on very thin film of oil so that they can make it smooth. So it's, the discrepancy is possible due to that. We also did some work on dynamic wetting to answer the question I posed earlier. This is the important mechanism for splashing, drops impact, wet, and then this film in the middle is a long, long way away from where the splash occurs. Blah, blah, blah. And the final thing was Leidenfrost, which I promised. Oh, sorry, Jack. Jack did some stuff on this as well in some absolute classic papers, which I can send you. Good. And the final thing we worked on with Leidenfrost. So this is a drop sat on a hot solid. Very similar things going on. You can measure the vapor film in here, its thickness, etc. Except for now you have to incorporate the fact that the solid is hot. Its heat transfer into the drop causes evaporation, which causes this thing to levitate. Okay, so So again, you can extend our model to this case. Let me just say the final one, and then I will stop for a break. This is more recent work where we've looked at, these are called, literally these are called hydrogel spheres, but for kids these are known as water beads. And they start like that, you put them in water overnight and they turn into that, so they're 99% water. And they also exhibit a Leidenfrost effect. If you chuck these, well, I'll show you the experiment. Frying pan, they bounce around because they're evaporating water and that's suspending the drops, causing them to bounce. Okay, so this was during COVID. I bought myself some of these, fired up the frying pan because I thought, you know, my kids, entertainment of my kids during COVID was not the most enjoyable part of my life. Some people claim it was a lovely part of their life. I'm not so sure. So I thought I'd do an experiment and that'll entertain them. So even I managed to do this experiment, so I'm sure you can if you want to. And that entertained them for about 40 seconds maybe. And then I put them on the iPad for the next 14 hours of the day. So we did some modelling, trying to understand the heights of these films. It's kind of interesting because when they're small, they're basically spheres, so they're high up. Then they get closer and closer to the substrate as they get larger. And then there's a different regime where they're very flat, so there's a lot of evaporation, a lot of surface to evaporate from, and then they get higher again. We could predict that transition. And that's basically it, I think. So lots of this is in an annual review, which is now available. And Peter's open source is there.